want to look at the power across, or a power dissipated or delivered by an element. Now, one of the things that I said here last time here is that we were talking about passive element. What's a passive element? It's when energy is absorbed by an element. And the way you see this here, that the way you can think about it is that, you know, in the electric field picture, we have this field right there. And what we imagine here is that if I have a test charge that's positive, this test charge will move in that direction. And so what we're seeing here is that this motion of this test charge represents the current, and then the field tells us that there's this force that's pushing it. So the only way you can push it is that if I have a higher charge density here that's positive and a negative density here, right? That's what we mean by a drift velocity across an element. And so what you're seeing here is that if I have a potential drop across this element, then that means that the current flows from it follows the field in this direction. And what we say here is that there's a loss of energy. Why is there a loss of energy? Well, if this is a negative plate, and that charge hits that negative plate, there's less charge. If there's less charge, there's less potential. If there's less potential, there's less potential energy in the system. So that means that it took energy away. But I like this picture. Why do I like this picture? Because if I have this picture, what happens to the charge? Well, it has high electrical potential energy here, and when that charge comes all the way down here, what did it lose? It lost electrical potential energy. Just like if somebody was skiing down a hill or whatever you want to think about. So when we have a passive element, the fact that there is a decrease, right? We say that this causes a decrease in electrical potential energy. And when there's a loss in electrical potential energy, we say it's passive. And like I said before, resistors, capacitors, and inductors are passive. And what's hard to sort of think about this is that it's very common for people to say, when you say a capacitor is passive, well, let's just think about that statement here. Does a capacitor have an EMF? Is there a way for a charge between two plates like this to come all the way back up by itself? No. Capacitors are passive. And as a consequence, you got to remember that, especially as we get further down. The only way you can have an active element if there's an EMF. So we come to the next piece here. So now if I talk about an active element, well, it's just got to be the opposite now. Energy is delivered by the element. And so, in trying to remember this, the current coming down from the positive to the negative guarantees that is a passive element. So if I have an active element, it's just the opposite. So if I have something like this, where I'm still at A and I'm still at B, and if I have some voltage across this thing, like this, then if I have current going in the opposite direction, something has to do that work to go from a lower to a higher. So if I look at these plates, I mean, physically, it totally makes sense. So if I have the same field here, and I have this charge coming up, there's no way in hell that charge can go up by itself. No way. Something has to do external work. The same thing happens in this picture. If I have a charge that's moving up this incline, you know there has to be work. And what happens here is that if this is my very simplistic view of a power supply, then what has to do that? The way you get charge moved up is that you have an EMF. And that EMF drives charge. So as charge comes down, the EMF guarantees that it's pushing it back up. And that EMF is what defines what is active. So therefore, you deliver power to the circuit or energy, right? It's this EMF that delivers power/energy to the circuit. That's what we mean by active. Can batteries, power supplies be passive? Absolutely. Right? That's what we call charging up a battery. Right? A jump start effectively sets one of the batteries to be passive while the good battery is active, and therefore you start the whole jump process. It's a very complicated picture, but that's what we mean by that. So what happens here is, like I said before, energy is challenging to measure in any situation, right? Energy is very, very challenging. So typically, most energy measurements are indirect. The same thing happens with circuits. If you were to look at how you measure energy, you'd have to somehow relate the voltage or the current to that. But what you'll find here is that in circuits, one does not use conservation of energy directly. But what is used is power conservation. Okay, so we do use power conservation because it's just easier to measure. Why is it easier to measure? Because now we're talking about power being what? Power is just going to be some function of time like this, and if I have to integrate this function, then I get the power. But if I measure the voltage and the current, I got the power. Now note, you got to be careful. This is a general definition. And this definition is what you would use for a power supply. Whereas resistors and capacitors and inductors have a different relationship. So you got to be really, really careful here. So what we find here is that you're going to see that this course, to a large extent, is how you handle your plus and minuses. And frankly, you shouldn't trust yourself because I sure as hell won't either. Okay? Plus and minus signs are the number one thing you gotta pay attention to. I kid you not. You're gonna be swimming in them. Just think about this. Imagine that you have 10 equations, 10 variables, and you got multiple minuses and plus signs. How do you know you didn't screw up? You're going to put this thing into your calculator, you're going to calculate it, and you're going to get the wrong number, and you're going to say, I did everything right. I doubt it. It's the minus signs. Remember what I said? I've been teaching this class for a long, long time. Pay attention to the minus signs. Super, super important. So what you find here is that if you look at the textbook, or you go online, this is what they say. Power has to come from where? From the power supply. All active elements that deliver energy we could say that the energy delivered must be the energy that has to be absorbed. That's what we mean by conservation of energy. But because I said before, energy is typically very challenging, what we do then is we talk about the power delivered by the circuit. The power that's active, all of the active sources must sum such that all of the passive elements must sum to zero. And this is a very common way of looking at this thing. And what I find here is that this then explicitly forces you to deal with the minus sign. So when I do it personally, I always say that all of the active sources must equal all of the passive. Now you gotta be careful with this thing here. This does not guarantee that the values of the currents and voltages are correct in the circuit. Okay? And it's sort of like conservation of energy. If you try to apply conservation of energy and think that you're going to get answers solely from conservation of energy, you're going to be in a lot of trouble. One very simple example, do you know what Newton's cradle is? Where you have a series of balls hanging from a string. You can actually drop one ball, it hit, and then two come out, according to conservation of energy. But you'll never see that. So what happens here is that conservation of energy is one constraint. In order to really solve the issue of Newton's cradle here, you got to apply conservation of momentum as well. So when you look at this does not guarantee that the current and voltages are correct. It's just one condition on the circuit. So you got to be careful on how you use this thing here. Okay, so what I'd like to do here is I want to do two examples. Okay, I want to do example 1 and 2, and then we move on to chapter 2. Okay, now erase the board. Now, typically I wouldn't do this, but I know that this is the start of a semester, and I'm just going to help you a little bit with this one. I may not do this whole example, but it's to sort of remind you is that when you start to integrate things, the very first thing you got to do is that you got to parameterize the curve. Okay, so the way I typically do this here is that I sort of like, now, is this an issue with shooting it on the whiteboard like this? Anybody have a problem with that? Should I lower the screen? If you don't say anything, then I'm not gonna do it then. So what you're seeing here is that, let me give you a little bit of moment to think about this. You have a current source. That's something you don't have experience with. So you have a current source, and that means that that source will produce a constant current. And I'll talk more about a current source here in chapter 2 here. But a current source is very similar to a voltage source. What does a voltage source do? It produces supposedly an ideal voltage source, puts out a constant voltage. But what happens to the current? It could vary depending on what you put in the circuit. A current source keeps a constant current, so therefore the voltage across it must change in order to keep that current constant. So here we go. So I got a source and I got a voltage. So effectively the voltage here must be the same as the voltage there according to Kirchhoff's voltage law. So it says here, so I got a current source and a voltage drop across that element. I want to determine the power as a function of time. So this is key right here, right? Time. Not a numerical value, but time. And then we want to get the energy absorbed. And then, sketch these. So what I want to do then is I want to go in and I want to calculate. What do I mean by that? So it turns out that this problem shows up in this chapter, and there'll be some others very similar in chapter 7. So I'll help you on this one a little bit, just to sort of like get you thinking. So what you see here is that I have to parameterize this curve here. Clearly this is a constant, this is a line. So when I get this, look at this line here, what I'm really trying to do is that I'm going to try to write this equation as what? This is the current, it's a function of time, right? This is the current source. And this equation, in order to completely describe this, I need what? It's slope times the time times the intercept. So my job is to figure out what is the slope, what is the intercept. And the same thing happens here. Okay, so let's do that. So if I want to determine the power, what I'm going to do here is that probably a good way to look at this thing here is that note, this is half a second, this is 1 second, so I got to break this up into intervals. So if I was to set up time, you could see that I'm going to be looking at the time interval between 0 and half a second. And then you can see that from half a second to 1 second, I get a different curve here. So if I look at this thing here, I'm just going to try to set up a table just to be organized here. So then, when I look at this guy here, well, I look at this voltage here. Let's say I talk about voltage as a function of time, and then I'm going to get current as a function of time. Clearly, I'm talking about the current source. That's the current in the circuit. So if I look at this voltage right away, you can see that this guy has what? That's half a second. So if I go and I parameterize this curve, you can see that the voltage here has what? Well, its intercept is 0. So if the intercept is 0 at this point here, then that means that the voltage has to be what? Some slope here. And you can see this slope has to be what? 3 minus 0, 0.5 minus 0, t, so that should give me 6t. So if I look at this guy, I have 6t for my voltage. And it's only valid up to half a second. Now if I look at this guy here, clearly this is a constant. So if I look at the current, you can see that that current here has to be, looks like it's of orders of 1 amp. So then if I look at this guy right here, what's the voltage for this guy? Well, we know what the slope is. What we got to find here is what? The intercept. So here we go. Do I know what the slope of this guy is? Yes. So if I look at this guy then, I'm going to see that I'm going to write this as V equals to minus 6t, right? Same slope but opposite, plus the intercept. So in order to get that intercept, what I got to do here is I got to pick one point along this line. And the point I'm going to pick is that one right there. And you could see here that the voltage at t equals to 1 second must be 0. Right? So then that means here that this has to be minus 6 times 1 plus b. So you can see that b has to be plus 6. So when I look at this equation of the line here, then that means I'm going to get what? Minus 6t plus 6. So I've now parameterized that curve. If I want the power then, as we already know, the power is a function of time. It's just this times this. So this is 6t. This guy should be minus 6t plus 6. Now if I do the rest here, right now I could go between, you could see that from 1 to 2, from 1 to 2, then I could I'm just going to just write it down. So if I look at that slope, so how about if I go from 1 to 2 seconds, then I'll just parameterize this curve, and what you get here is you get minus 6 plus 2. Nope, I'm sorry. I'm looking at the curve. This is minus 6 plus 2. And then the other one here is that, so obviously this power has to be 0. And then to get these works here, what do I got to do? All I have to do now is that I have to integrate the work. The power. Right? The work as a function of time should be that guy right there. Right? That's the definition of the energy of the circuit. Yes, sir.
I don't think it matters because we're multiplying by 0, but should that be minus t plus 6?
Yeah. Yeah, this should be a t.
Just a regular t plus 6. Because in the current one, you're going down by 1.
Yes, sorry about
And
that. You're absolutely right. So it's just t. I guess I'm carrying that 6 with me as I go along here. Like, so for example, if I integrate 6t, it should be what? 6t squared divided by a half, so I should get 3t. If I integrate this guy here, it should be what? If I integrate this guy, I'm going to get minus 3t squared plus 6t. And then I could then go in and I could, write these functions down. So if I just plot these functions right here, so if I plot the power as a function of time, it looks like I'm going to get a straight line. Well, I'm going to get really this guy right here. It should be this because I'm multiplying by 1. So my power should look like that. Right? Where it breaks off like that. It should be exactly the same. Yes?
For the top right, it should be 3t squared.
Yes. Okay, any other small errors here? Just to make sure I get that. And if I plot this guy here, you can see that this is quadratic. So, let's see here. So if I'm plotting the first piece of this guy, it should look something like this, right? Because that's t squared. If I look at this guy, that negative sign is going to dominate at larger values, so it then should start, tipping over like this. So I'm assuming that it goes something like this. By the way, I'm talking about the energy. Now note, that's to help you. I think you have 1 or 2 problems like this, but it's just to remind you about the equation of the line. So let's go to the next one. So what you have here is you have a circuit, and the circuit has elements. And one of the things that you got to remember here is that if I have current going this way, and it's positive, it's going that way. But if I have current that's negative in this direction, it really means that it's going the opposite direction. Okay, so you gotta be careful. And maybe you could think about plates, or maybe you could think about inclines. How is the incline changing the direction of the current flow here? So use conservation of power to do this. Now I should be really careful here. I'm going to give you a circuit on Monday, and you'll have resistor values and voltage sources. If you use KVL, or and not conservation of power, if you use, I mean, you gotta use some KCL, but if you're trying to use any of these like circuit methods where you're using KVL, KCL, Ohm's law, and stuff like that, I'll probably give you 0. Because if you want me to bring in stuff from chapter 3 into this quiz here, I'll gladly do it. And I'll make sure that you all get 0. Right? So we want to only use the techniques of chapter 1 here, not chapter 3. And it's important because when we get to circuits that are super complicated, this then becomes a useful technique to say, like, does this even make sense? Okay, give it a go. Tell me if this circuit is possible. And your job, really, more than anything else, is to identify what is passive, what is active. That's what this is about right here.
Can we assume that the current through 2 is the same as
Yes.
2?
If elements are in series, then they should have the
But
same
then,
current.
well, I mean, 4 and 5 are different.
Are they?
Oh, right. It's different direction.
So we're pushing it negative.
This is wired in series. So I can just rewrite it like that. Okay, that makes sense.
So they're negative 2, right? Basically. So
5. Shit, that wasn't 3, that was
4. You got 5 amps.
Hey, let's do this thing here. I think we should do them right in order. So if I write them like this, all of these quantities will be positive. All of these quantities would be positive. No negative sign. So ultimately, we're asking this question. Is all of the active energy being absorbed by these passive elements? If these two are equal, then that means that the conservation of energy, conservation of power says that this circuit is a go. If it's not equal to each other, then the circuit is not possible, right? It's the exact same thing as the Newton's cradle with the ball. So here we go. Let's go through 1, 2, 3, up through 5 here. So what you're seeing here is that I have a 2 amp current here, so that means there must be 2 amps going through here. Now, if you look at 2 here, you could see that the current is coming in the positive end, so 2 has to be passive. So then I'm going to walk over here, I'm going to say 2 is passive. Now if I look at here, you can see that the current, because they're in series, does have the same value of 2 amps, but now check this out. I have 2 volts across 1, but that negative sign then implies that they switch. So the drop across this guy now is 2 volts in that direction with the positive sign. So therefore, 1 must be active since the current is coming in through the negative terminal here. So in this case here, I got P1. Okay? So now let's go to 3 here. So this one's straight up because you could see that the current of 3 is coming in through the positive end, so 3 must be passive. So I come over here. Now I go to 4 here. So if you go to 4 here, it looks like that current, because it's being negative, really is going in which direction? That direction. So if I look at this 5 amps, it's going through here and it's going like that. So you could see here that that current is entering the negative terminal, so therefore this must be active. And then we're left with 5 here, and you can see that the current is definitely going in through the positive, coming out the negative, so therefore I have P5. So now all I do is I multiply the numbers. So if I multiply the numbers, I don't look at any signs now. So 1 has to be 2 times 2. 4 has to be 5 times 4. So therefore, I get 24 watts. And if I do the exact same thing for 2, you could see that this is 5 times 2. 3 tells me it's 3 times 3. And then finally 5 here is 5 times 1. And that should give me what? 10, 19, 24 watts. So this implies here that I get 24 watts equals 24 watts. That means that the circuit is a go. Conservation of energy, conservation of power says that it's possible. Okay, let's go to chapter 2 now. So if you read the textbook, you're going to find that this chapter has some very, very theoretical ideas. And I'm sure there's going to be ideas that you're not going to like. I mean, there's some stuff that you kind of go like, what? So what we're going to do in this chapter here is that the first thing that we got to really think about here is that we're going to start looking at what types of circuits that we will deal with in this course here. And the answer is we're going to be dealing with linear circuits. And probably the most important thing that we really care about is called superposition. So I want to introduce the concept of superposition. By the way, superposition also rules Newton's second law when you talk about the net force, or if you're talking about the net electric field, it's the exact same type of idea. And then what we're going to do here is that we're going to model resistors, and we're going to also model ideal power supplies, that is voltage sources and current sources. We're going to talk about independent ones. And then lastly, we're going to introduce a new type of element that you may or may have not seen before, that is called a dependent source. And that's the thing that I'd like to hit before we finish this class today, because that might take a little bit of reading and trying to understand what is being said. And like I said, if you read the book in that section, yeah, you'll see what I mean. There's some pretty deep concepts there. Yes.
But it's not like the physics book where they're like simplifying it too much. It's just
What do you mean?
counterintuitive. Like you before, when you talked about the physics book, you used to say like, you know, like they say this, this, and this, but they're wrong. They're lying to you, and you tell us what was up with it. Is it the same deal with the circuits book?
Hopefully, I'm not saying that they're lying.
I've heard you say that.
There's some things I totally agree. Right? If you're talking like in 4C with Snell's law, oh hell yeah, that book is totally off the mark. I completely agree. They're not off the mark in this book.
Okay.
But it's just going to be really, really counterintuitive. And you'll see, I'll give you a little bit, a snip of what the book tells you, and I'm gonna say, ignore that. Because you'll never see that in any problem in this course. So here we go, chapter 2. And so what we're gonna be looking at is circuit elements. And so like I said before, is that we're asking the question, the type of circuit, type of circuits we solve, and this is really linear circuits. And the other thing that I really need to hit here is that we need to talk about independent sources. And you're going to see they're going to be both voltage and current. And I'll explain a little bit more what a current source, but over time, you won't treat the current source any different than you do a voltage source. And then the other thing that we got to do is that we got to talk about dependent sources. And you'll see that dependent sources come in 4 flavors. Okay. So here we go. So let's talk about linear elements, or linear circuits, excuse me, right? No, linear elements I want to talk about. So there's really 2 things that we could think about when we talk about linear. One is we can call it the superposition. And there's another thing here called homogeneity, which is really a scaling law. I'm not sure if that's the way you spell it, so I'll put quotes around it. So what you'll find here is that I won't cover this one, but I'll definitely cover superposition. And this comes back in chapter 5, and it becomes a really important solving technique in certain situations. And what you'll find here is that, so if I have an element and I have some voltage across that element, then we know that we'll have some current flow across this guy. So in essence, what we could say here is that the voltage across this element has to be proportional to the current. Now note, I'm being sloppy in my notation. It really should be a difference in potential. But remember the definition. When we say voltage, we imply that it's a potential difference. And technically, I should be writing it like this, but we're lazy, so we write it like that. But that's what I mean. So when I say this voltage, I really mean the difference between that node and that node. And that sort of makes sense right there. Now, what's interesting about this thing here is that when I look at superposition, I could have a circuit that maybe looks like this here. Maybe I look at something, let's do this. And let's say that I have some resistor, just for the sake of argument here. Let's say that I have V1 and I got these elements here and I have this circuit like that. So according to this circuit, that means then that this voltage must produce a current right here. And the current that this voltage produces, I'm going to just pick an arbitrary direction, but since I've had lots of practice, I know it's got to be like that. So what we say here is that this voltage applies some current here, and it's scaled somehow, depending on what these elements are. So far, so good. If I have a linear circuit, so now a linear circuit implies that if I change this circuit and I now add a second voltage source, regardless of where it's put at, let's say I put it right in here. How about if I do it like this? And I call this V2. Then that means when I look at this resistive element, there's going to be two currents. There's going to be a current produced by voltage 1. And depending on how I have the source, I'm going to have a second current right there. So by adding V1 plus or minus V2, this must be proportional to that. So by adding this other element, that guy changes the current proportional to the voltages of these two sources. If I can't do this, I don't have a linear circuit, and therefore I can't really use the techniques that we're using here. That is an assumption that we're talking about here. But that's what I mean by superposition. Superposition tells me that the sum of the sources will then be the sum of the currents across this element here. And I'll just draw the current going down here just for generic purposes. So here we go. So then if I talk about a resistor, so let's model a resistor. Now, I'm assuming that you guys are all experts at resistors after Physics 4B, and what we know here is that the resistance depends on what? Resistivity. It depends on the length of the resistor, right? And it also depends on the area. It also depends on the temperature, but we hope that it doesn't change it too much because we need that to be linear, right? So we could go in and all of these details define resistance very well here, right? Resistivity, well, let's just leave it. So this is the material thing, and then that's just the size and width of that resistor. So if I have a resistor, that means when I look at these nodes from A to B, and I have some voltage drop here, then that means that if I have a voltage between A and B, I'm guaranteed to have a current AB across that, such that the voltage across that resistor is then going to be given by this quantity right here. Right? Resistors are passive elements. Right? These are passive elements because they dissipate power. And if I don't have much of a temperature change, you'll see that I could come in here and I could plot voltage versus current, and I'll get what? I'll get that linear line. It's a linear element. That's what we mean by that. Are capacitors linear? No. Are inductors linear? No. Only when you get into AC do we then start talking about capacitors and inductors being linear. So I typically don't write AB, I typically write the value of the resistor for this thing here. Maybe I should have put an R there. And because these are passive elements, the way we typically write power across this resistor is that we could either write this as voltage times the current, or we could write this as voltage across the resistor divided by the resistance, or I could write this as the resistance times the current across that resistor squared. Right? That's how we can define what we mean by power. So what I want to do here is I want to move into the next example here. And one of the things that you're going to really struggle with this course here is signs. The book, from my experience, is going to do whatever it can to screw you up with the signs. And let me show you, this is an actual problem from the book. All right. And let's look at this next example here.
No, let's stress the squares.
So what you're seeing in this problem right here, this example problem, is that you have a voltage source, and you have a couple of resistors, and the one thing that I would expect you to know here is that elements that are in parallel means they have to have the same voltage. So the fact that this is 150 volts means that the voltage across both these resistors must be 150 volts. So what I want to do here is that this is a fairly straightforward calculation here. It says calculate the current and the power absorbed by each of these resistors. And it says, note the polarity across these resistors. If you note the polarity across these resistors, this guy's going downstream, as we could say. This guy's going upstream. So immediately, what you find here is that that resistor follows the passive convention of resistors, right? That's what we mean, right? If you've ever touched a really hot resistor, you won't forget that they're passive. This guy's doing something funny here. So what do I mean by this here? Well, let's go through the very, simple calculations here. So if I go in here and I look at that, so what I typically do here is that my notation is I always try to keep to the book's notation if I can. If they label this I1, that means that's got to be V1, P1. If this is 2, that means it's got to be I2, it's got to be, V2 and P2. So when I look at resistor 1, if I'm asked to calculate the current in each of these elements, we immediately see here that in the first case here, they're in parallel. So if they're in parallel, that means that the voltage across one must be 150 volts. So then if I go look at the current, it must be, according to Ohm's law, be given by this guy here. And like I said, this is a fairly straightforward calculation here. We could see here that this gives me then 3 amps. So the current of 1 must be this, and therefore the power I could calculate numerous ways. but I'll calculate the power probably different than you here. But if I calculate just by multiplying the voltage and the current, then I'm going to get what? I know that the voltage is 150 volts, the current's 3 amps, so I get 450 watts. Is that a lot of power? Yeah, it's a lot of power. Right? Do you know what resistors typically have as far as power is concerned? Quarter watt. And this is 450 watts. This is such an unrealistic question, right? If you did the resistor in water, those guys are about, I think they can handle up to about 10 watts of power, I think? No, maybe a little bit more. Maybe about 30 watts of power, I think is what they're at. So that's one hefty element there, no doubt about it. Well, let's go to resistor 2. So if I look at resistor 2, we already said here that because these guys are in parallel, it must have 150 volts across it. But now, what do I know about the current here? That current here is negative. It's not positive. Right? So using that non-passive convention tells me that I do calculate the way I use Ohm's law, but now I got to put in by hand what that current is here. You know, once again, if I do this here, we could see here is that if this is 3 amps at 50, if this is half of that, that means I can multiply this by 2 here, so I'm going to get 6 amps in the negative direction. So if I then go calculate the power, well, the power has to be what? Well, if it's a truly passive convention here, we know that power, I could calculate this multiple ways here, but we know that can't be true. So if I use this definition here, right, I should have called this 2 here, we know that in the end, it can't have, it can't be delivering power, so therefore, this guy has to be 6 squared times 25, which then gives me a value of positive 900 watts of power. Right? It has to be passive. Even though the current is in the opposite direction, the power must be a positive element because it's being passive. So remember, once again, if I calculate a power greater than 0, it's passive. So let's move on and talk about the next. Yes, sir.
Could we say that the voltage drop is negative 150 volts?
Yes, you could have also done that. That the only way you can get that, I could have also done negative voltage because that's the only way it could flow. And then if I multiply the negative current, then I would still get the exact same thing. So what I want to do here is that I want to go in and talk about sources. So I want to talk about independent sources. So independent sources. Active devices always add energy to the circuit here. And So what we find here is, so if I have an active source, so let's talk about a voltage source. So if I have an active source, look at the current. Where is the current coming in? It's got to come in through the negative here. Right, so look at the sign of that voltage. That means that the current coming into this element must be in the negative terminal. When you have this, then we call this an active voltage source. Okay, it's an active voltage source. If I have the opposite case, where I have current coming in this direction, then this guy must be passive. So that means that battery is absorbing power, like the recharging of a rechargeable battery. In this case here, I could have one of those, standard AAA batteries that does supply energy into the circuit. And in a very analogous way here, I could also have current sources. By the way, we should be careful with language here, but one of the things that you should hear this, let's see here. This is a voltage source when it's not connected to anything. As soon as you connect it to something, as soon as you connect it to a circuit, it's not a voltage source anymore. It's a power supply. Why? It delivers voltage and it delivers current. Only when this thing is open like this is it a voltage source. So even though you'll say, that's a voltage source, that's not correct. So in a very analogous way here, I could also have current sources. Now let's look at the current source here. So if I have a current source, let's call it IS, and I want to make it active, then what I do here is that the current has to enter what side? The negative side. So check this out. So then it has to be like that. Look at the current. It's hitting the negative. So then this would be an active current source here. But if I have it, the voltage drop the opposite way, right? So if this is my current source here, but if I have a drop that goes like this, then that means it's got to be passive. This becomes pretty important in chapter 4, by the way. Okay, this is a really simple thing. Look at this sign convention and remember what we mean. Coming in through the negative terminal, it's got to be active. Otherwise, it's passive. And that's a very slippery thing that students seem to not internalize until it's in your face a couple of times. So let's talk about that. What do we mean by an independent source? Okay, what do I mean by an independent source? Well, what I mean by an independent source here, so if I have an independent voltage source, let's say like we have a 9-volt battery. What do I mean by that 9-volt battery? An ideal 9-volt battery means that it's going to hold that voltage fixed regardless what the current in that circuit is going to do here. So what it does here is that this guy always puts out 9 volts regardless of the circuit load. It's always going to put in 9 volts no matter what. In other words, suppose I have a circuit that looks like this. And then I change that circuit. So now I have 2 elements. Does that change the voltage across that battery and what's it putting out? The answer is no. I mean, I may get different load voltages across these elements, but it's always putting out 9 volts. So what you find here is that what changes here is that the currents are variable. Depending on what you put in those loads will tell us what currents you get. So the currents can vary, but the voltages can't. The same thing happens with current sources. And what you find here with the current source is that if I have an independent current source, that means I have a fixed current in some circuit. So for example here, if I have a circuit that, let's say, has 5 amps, and I have some element here, then that means I'm going to get 5 amps through that circuit. So that means no matter what, I get 5 amps. It's going to always put that out. Now, if I now add an element to the circuit, even though I may double the load, that circuit will still have 5 amps. It's independent of what the load is. So there has to be a trade-off. If the trade-off here is that in order to keep a 9-volt constant source, then that means that the currents have to be variable. So in this case, what has to happen? The voltage has to vary. So in these cases here, what you're seeing here is that the voltage across the source varies. Source is variable. I don't want to say variable for some reason. So that's what we mean by an independent source. It's the same no matter what here. Now, one of the things that we should sort of like try to think about here is that to give you an example of this, I want to go in and I want to sort of like talk about, the next example, because I think this next example really shows you how counterintuitive you could have with a current source and a voltage source, and part of it is because you don't have that experience. So let's look at this example here. This thing is not very good. There it is. So look at this circuit here. I think this is a really good example. Okay, so what you have here is that you see that I have a current, a voltage source, and I have a resistor. And one of the things that we want to remember here is that anytime I have parallel elements, they have to have the same voltage. So if this is 15 volts, that's 15 volts, that's 15 volts. So then it says, suppose that the current is 3 amps, then I want to calculate the current through the resistor here. And then what's going to be, what I really want to look at now is that I want to calculate what that current through that resistor is when I now change this source voltage to be 5 amps. So since we got about 15 minutes or so, I want to just go ahead and do it right now. Because I want to at least try to talk about dependent sources a little bit, because remember what I said. Dependent sources will be on that quiz. Okay? And I'm not going to be able to get to them very much, I may not even at all. But if you follow my notes, you'll see that the way this book does it, it starts them very early, which I'm very happy, so that it's like demystified as you go along. Most textbooks don't, they just jump into them and they're doing topics stuff like that. I like this approach that the book takes. So what we want to do here is that I'm going to redraw the circuit here. So if I look at A, what you're seeing here is that I have a current source that's 3 amps. I have a voltage source that's 5 ohms. And this is 15 volts. And our goal here is to calculate what this current is doing here. So I'll call this IA. That's what we want to calculate. So one of the things that we see here is the fact that these two are in parallel implies what? Well, it implies here that if these two have the same voltage, so the fact that this tells me that the voltage across the 5 ohm resistor must be the same as the 15 volt source here. Right, so the source, that looks like 5 and 5, but it really is an S and a 5. Hopefully that's clear. There's 15 volts, so according to Ohm's law, it must be what? The resistance of 5 times the current A. And you can see right away that this current has to be what? 3 amps. So if I look at the circuit, I have what? I have 3 amps coming this way. And here, I also have 3 amps. So how much current is through the voltage source? 0. So that means that the current in this branch here has a current of 0. So how much power is being added by the power supply? 0. So what we say here is that the power supply V source equals to 15 has a power of 0 watts. And when this happens, we say that the power has been shorted out. Okay? And what we mean by shorted out, if you ever do this in the lab, which I strongly encourage you, in fact, you will do it next week. It's mandatory in the lab. You're going to take a short and you're going to go across a source here and you're going to see that there's no power coming out of this thing. Even though it forces that guy to be 15 volts no matter what. So it's the rest of the circuit that really determines what actually happens here. I can't just isolate this guy here. I can't just isolate here. But what happens here depends on all of the elements in the circuit. So now we go back and we now change the source to what? 5 amps. So what happens to the current across the resistor? So what happens to that resistor?
The current stays the same because the voltage is the same.
That's right. The voltage stays the same, so therefore the current across B must be 3 amps. But you could see here that as the current is flowing, now I have what? 5 amps coming this way. So what has to happen at this node right here? So if I have 5 coming in, 3 going out, that means I must have 2 amps going that way. So what am I seeing? Well, which is the active? Which is the passive source here? So if you look at the first guy, you can see that the voltage across that 5 amp must be minus plus. So therefore, the 5 amp source is active. But if you look at that 15 volt source here, you could see that the current is coming in the positive node. So therefore, the 15 volt source must be passive. And so even though the current doesn't change, you could see that what these sources do really do change depending on what that value of the current source is. Yes?
In the first scenario, is the voltage source active or passive or neither?
It's shorted out, so it's not passive or active,
Okay.
right? Because when I say shorted out, it means it's not delivering or absorbing power. So we then say neither in this case here. Right? It can't be either. Elements are either going to absorb or they're not going, or they're going to deliver. If they do either, then it must be a short, as we would say. Now, one of the most important tools in circuits is a short and an open. Okay? Now, I am not used to this room, so I feel like I'm walking back and forth looking for this little dude. So, what we want to look at here, very briefly here, is we want to talk about open and open circuits and short circuit. And what you're going to find here is that when I talk about a short circuit, what this implies here is that you got to look at the voltage across a wire. So what I ask you to do here is that sort of like imagine the voltage across a wire. Well, what that means here is that if I have a voltage across a wire, the fact that the resistance of a wire is equal to 0 implies that the voltage across the wire must be 0 as well. But what about the current? Current could be anything it wants. What determines the rest of the current? Is the rest of the circuit. what determines the current through the short depends on the rest of the circuit. Now, if you have an ideal power supply, you would then get infinite current. But that's not possible, right? So if I have a real battery, so if I have a real source, you could imagine here that I have some internal resistance here. And if I have internal resistance here, if I put a short across AB, that current has to be the current of what? Of the internal resistance. And this is what we call the short circuit current. Right? So if you look at the power supply, you'll see that there's one power supply that I think it could put out up to about 5 amps, I think it is. I can't remember. So if you short that power supply in the lab, then that means that short circuit current will be 5 amps. If you short out some other power supply, you'll see that some of them will actually stop producing current at about, I think it's half an amp or 500 milliamps. So when I talk about this short circuit current, that's exactly what I mean here. Now, so then that picture's here. So if I short circuit a voltage source, that means what I'm really doing here is that I have a wire like this, and this voltage source has to read exactly 0. Right? If I short out a voltage source, an ideal voltage source, then that means the drop across that thing is 0 here. And so what you'll find here is that I could have any current. So this current here coming through this guy we say that this current is determined by the rest of the circuit. And so I could say the exact same thing, what I mean by an open circuit, for example. So now, if I have an open circuit, what I'm looking at here, I imagine that I have a current source. If I have a current source, let's say that it's moving in this. How about if I keep my voltages in the same direction here? So if I have a current source that's coming like this, and I open this current, what you're going to find here, that what I'm really doing here is that I'm essentially saying that I'm equating this thing here with an open like this. So if I open this current source here, what we would expect here, how much current is actually flowing through the open? Of course, nothing, because it's open. So here, I would say that the current of the open circuit must be 0. However, there's still a voltage drop across this guy. So if I open up a circuit where I have a current source like this, I can model this current source here by thinking about this guy of having a source value of 0, but now this voltage could be anything. And what determines that voltage, that open circuit voltage? It's the rest of the circuit. So in this case here, we say that this voltage of the open circuit is determined by the rest of the circuit. How much time do I have? None. Damn, what I really wanted to do is I wanted to do these applications of what that means. So we got one thing that you gotta do is that you gotta make sure that you do the dependent sources. And I'll tell you that there will be a dependent source in that quiz on Monday, okay? Now, I know this seems kind of harsh, but believe me, when you see the rest of the chapters, you'll see why I'm rushing through these as much as possible. So if you're in the Friday lab, I'll see you on Friday. Homework is due Monday. Quiz starts at 9:30 a.m. Okay?
Monday morning.